Hi everyone. Everyone can hear me? Yeah, cool. So today I'm here to talk about this approach that is called Evals first, code later. It's a way to build applications, AI applications, which takes them from demos to real production products. A little bit about me. I'm Saksham. I run this company called Literate AI. We help companies instrument third-party SDKs without requiring much of developer bandwidth, and we are backed by Entrepreneur First. I've graduated in bits in computer science from bits, and my interests generally include retrieval systems, prompts, eval systems, synthetic data generation for training models, etc. So let's dive straight in. But before that, I want to borrow this concept from an talk by Andrej Karpathy that he gave in YC AI Startup School, where he explained how software has evolved through the decades, right? For example, in software 1.0, we used computer code to program the computers. And then in software 2.0, we use weights and biases to program a neural network. Now we enter this sort of new computing paradigm where we use prompts. And in a way, we can sort of think of making a custom neural networks with prompts, right? We can make it, and with the help of LLMs, we can make classification, segmentation, anything that we would want to. We sort of have our custom neural network at place, right? But now, surprisingly, it's in English, right? A lot of times, an example of that is in software 1.0, we used to have like positive example, negative examples, and write code for that. And in software 2.0, we sort of have a lot of positive, negative examples, and then we train a neural network on top of that, and we get the parameters. And in software 3.0, we sort of just write it in plain English that, hey, these are some good examples, these are some bad examples. But now, since these are new computing paradigms, we need new ways to test those things as well, right? So in software 1.0, we used to write a lot of tests with the help of unit tests, regression tests, etc. And in the next era, we used to split our training data sets into test set, validation set, etc. And now we have sort of our internal benchmarks or some public benchmarks, and also some preference-based benchmarks such as LM Arena, which used ELO rating as same in chess.com. Now, I want to be clear about what is an AI application. According to me, it is a piece of software that has outsourced intelligence to an API call, right? And how many of you have built an AI application which involved a call to an external LLM? Yeah, a lot of you, right? And from my experience, when I started building such kind of an application. What happened was, let's say a prompt is working for 5 use cases, and then for a 6th use case it breaks. I sort of changed that prompt. Now it's not working for the 3rd use case, and now I changed that. Now it's not working for the 2nd use case. So now I'm in the vicious cycle of prompting again and again, and not knowing what is happening at all. So my attempt today is to go from this approach to a very systematic approach where in software development we have tools for testing and evaluation. We should have these tools in the AI application and processes for evaluating quality, which means writing tests, having some heuristics around it, and also for debugging issues, having custom data dashboards to look at the data that is production data or offline data, and also changing the behavior of an application, which involves fine-tuning, prompt engineering, adding tools, etc., etc. Many teams often start with the 3rd one and keep changing the behavior without focusing on 1 and 2, right? So today we'll not do that. We will move from this deploy first, pray later approach to a evals first, code later approach. Yeah. So we'll do that with the example of an application called PaperPie. It's a chat with research paper application. I'll first explain the basic architecture and some evals around it. What are the metrics that we are going to track, and some of the techniques that we'll use to make it better, right? And these are some of the technologies that we are going to use, and we'll track all of these metrics. I'll explain what are them later, right? So let's start with an overview of the basic architecture. So firstly, we'll have our indexer. What do I mean by that is, we'll have a document store. A document store is a collection of a lot of PDFs, which are our research papers, and then we take each PDF and pass it through a chunker. What does a chunker do is, like you can think of it, it breaks the PDF into multiple paragraphs, into multiple text chunks, right? I'll take an example where I do a fixed size chunking, which means I break the page or a essay into equal size of paragraphs, right? And then I pass all of these text chunks to an embedding model. Now, what is an embedding model? You can somehow think of it as a model which takes a long piece of text and convert to a fixed series of numbers, which we also called an array or a vector, right? And somehow magically it encapsulates what it means. So somehow it encapsulates semantic meaning of that sentence in those specific set of numbers, right? And what happens is, if we project these numbers into a vector space, we find out that similar kind of words are very close to each other. So this is a unlock that allows us to actually build a lot of semantic search applications on top of this. And so if you see in this slide, a lot of similar words like tower, gate, building, skyscraper, roof, building, etc. are very close to each other. So how this comes into our play is, what we can do is we take the user request, we pass the user query to an embedding model, and we get a series of numbers. And now we can look out what are those paragraphs which are closer to the user vector, right, in the embedding space. How do we do that? There's this thing called vector databases which helps us with the similarity search, or finding out which are the vectors that are closer to the user query, right? And we do that with the internally. What it does is, in a very basic sense, it's a cosine similarity score, which is a dot product of these two vectors. And then we have a threshold that, hey, x is a threshold, and any vector around it, if that is nearer to this user query vector, give me that. And then what vector store does is, it gives us some retrieved documents, and what do we do is, we then pass it on to the answer system. Answer system's main job is getting the user query, getting the retrieved documents, which contains a lot of paragraphs which have answer to the user query, and we pass it to the LLM and say, hey, this is the user query, this is the retrieved documents, please format an answer to this question. And if you don't find an answer in the retrieved documents, just say that I don't have an answer, right? This is a simple job of answer system, right? And what this is how the whole diagram looks like. So what we'll do is, we will separately evaluate search system and answer system, and that would help us gain more clarity into how our whole system is working, right? So what were the inputs of search system? It was a user query, and the job of search system is to retrieve very relevant documents to that user query. And the job of an answer system is to format an answer and put it in a very human understandable way, very simplistic terms. And if it doesn't have an answer, it should say I don't have an answer, right? But for that, we need a lot of these pairs, right? We need user query, we need correct relevant documents for that user query, and what does a correct answer look like? So we don't have that. We don't have any users yet. So what we would have to do it, we would have to generate all of this data. We'll do a synthetic data generation small just to get started. And once we have some users, we can use the live data as well. So how do we generate this synthetic data? We take our 5 golden research papers that are top examples, and then we chunk them through a chunker. And what do we do is, we take each chunk, we pass it to an LLM and say, hey, use this chunk and generate a question which has an answer in this chunk, and also an answer which answers this question, right? And we can also put a critique LLM on top, where we say to evaluate, hey, does this question, this chunk, and this answer, are these 3 coherent to each other? This is completely optional, but yeah, like this is an example of a synthetic data generation prompt that I have used. I have given him given the LLM a text chunk, and also asked it to generate some questions in a JSON format, which contains an answer in this chunk, and also an actual answer, right? And also a question type. It's a factual question, conceptual, analytical. You can have your own types based on your application. This is an example of a sample output of an LLM. I can show you the code as well here. Yeah. So this is a synthetic data.py file, and what we have done here is we have used this generate QA pairs where we have chunk text. We give it a chunk text and asked it to generate questions, right? Let's move on. And for evaluating search system, we'll do three metrics as of now, which are called precision, recall, and mean cosine score. Now, what do they mean? Let's take an example of a food recommendation system. Let's say you are on Swiggy delivering, getting a food item delivered, and it recommends you a couple of things. Let's say it recommends you a 6 things, right? Out of those 6 things, you only like 2 things, right? So it means the precision is 2/6. Out of the items that Swiggy recommended me, how much were actually likable to me, right? So the precision becomes 2/6, 1/3, which is 0.33. And since it is out of 6 items, it is called precision at the rate 6. If it is out of 10 items, it is called precision at the rate 10. And if it is out of k items, it's called precision at the rate k, right? This is an example of precision at the rate 10 and precision at the rate 5. This is a pseudocode for calculating precision. And now let's move on to recall. Recall is a little different from precision. Recall means, let's say there were 8 food items that I really liked. Out of those food items, how much was Swiggy's food recommendation system able to recommend me, right? So what does that mean? For example, it recommended me, let's say, 10 items. And out of those 10 items, how much were my favorite item present in those 10 items? So out of those 8 items, only 5 were present. So my precision, my recall at the rate 10 becomes 5/8, right? And recall at the rate 5 or recall at the rate k becomes, in that case, where I only have 3 items out of 8, it becomes 3/8. So it is somewhat how much was it able to recall out of all the items, right? And this is a simple pseudocode for recall. And remember, when we were searching through the items with the user query, we were calculating dot product. And what dot product gives us is, it's sort of vector databases gives us this cosine score, right? It's always good idea to log a mean cosine score, and it doesn't help directly, but in some cases, what happens is a lot of user queries goes unanswered, and we can calculate, hey, what are some user queries that have no information in our index store around it. So it helps us to know where the information gaps are, where what kind of documents are not present in our database. Where the mean cosine score is really less, it means our vector store lacks a lot of these documents around these user query, right? And now let's move on to answer system. Since answer system is a little subjective, the answers are very subjective. So the ways to evaluate it are a little sometimes non-deterministic and also deterministic. What I've learned, what we do in it was these 2-3 things that were really working for us. First was this unit test. So this is just an answer system that we have discussed. The format of an answer system is it gives text and also gives citations. What are the things that it has used to generate those answers? This is a sample unit test. So for example, the user query is when was the iPhone launched, and if my PDF contains an answer, it should actually, we can write a unit test that helps us know expect assert.match contains 2007, and if the answer doesn't exist, it should say that I cannot found, there is no information. And similarly, this is a fact Q&A feature. Let's say you have a fact Q&A feature in your chat with research application, and one thing you don't want is you don't want any user input to get leaked. So you can also check with the example of assert statements if there are no UUIDs or no S3 URLs or private URLs, file paths that are being leaked over here. We can do this for summaries as well. Let's say I say summarize in 2 sentences. Does it actually takes 2 sentences? We can do this with the help of assert and calculate full stops, how much they are. And also, if it asks to summarize something that does not exist, it should say that this doesn't exist, I can't summarize. So now what you can do is you can turn every user request, every failure case into a unit test. And now every time you change a prompt, you can run these unit tests and you know which prompt is failing for what use case. If a prompt has broken a fact QA, if a prompt has broken summarization feature, etc. So this was all about unit test. Let's go to this new thing which has emerged called LLM as a judge. so this comes with an asterisk. Sometimes it works, sometimes it doesn't. But what happens is a lot of times verifying an answer is actually a lot easier than actually writing an answer, right? So it requires lesser intelligence to check an answer rather than to solve a question. So that's why sometimes this works. This is the heuristics behind why this proves to be valuable. So we take another LLM and then we take the response of one answer. We take the response generated from the master LLM, we pass it down to a smaller LLM, and then say, hey, is this answer correct? Is this answer fluent? Is this answer factual or not? What is the tone? Is the tone aggressive, simple, easy to understand? And these are some evaluation frameworks that people have come up with. There's one called Ragas, it's an open source, and there's one by Deep Eval also, Langfuse, there's also. So these are some of the evaluation frameworks that are in the market right now. Um, some of them are open source. Luna by Galileo is closed source one. And yeah, one thing that we have noticed is you should always log sources versus cited. What do I mean by that is sources is the retrieved documents, what documents were shown to the language model, and cited is what documents LLM was able to actually use or reference in its answer. Sometimes what happens is LLMs tend to prefer certain kind of documents and ignore certain kind of documents. This helps us find out gaps. Hey, what kind of things LLM just ignores even if we give it to them. And these are some of the eval results, sort of a unit test result that I have done. So I can show you the code for it as well. I think something broke. Yeah, we are back. Yeah. So, so this is a run evaluation file that I have made, and this is a PaperPy repository that I will. It's a public repository. I will give the link to you guys at the end of this talk, and it has multiple different ways to run an evaluation. So let's run a simple um, evals/run evaluations. It's a quick evaluation, which means it will take only 5 examples. And there's also, it will use a fixed character chunker. So I have implemented fixed character, recursive chunker, and a semantic chunker. So it will go on and do the RAG evaluation for us. So it is going to evaluate 10 pairs. Meanwhile, this is kind of the result that looks like. It has precision at the rate k, recall at the rate k, f1 score, mean cosine score, and in this case, the k is 5. And also, it also calculates answer eval results, where we have LLM as a judge score, we have latency, and depending on your use case, you can add token cost, token size, etc. I'd like to talk about this F1 score also. F1 score is harmonic mean of precision and recall. It kind of encapsulates best of both worlds in a lot of cases. Yeah. So I think we are 70% done. We'll come back to this later. Yeah. And now let's improve this application. What we can do is we can have different methods for chunking. We can have different kind of embeddings for retrieval, and we can also have reranker semantic caching. What all of this means is I'll talk about it right now. Earlier we were doing fixed size chunking, and what is the pitfall of that is sometimes unrelated sentence got chunked together, right? So let's say a paragraph starts somewhere, it got cut off in the middle, and so a lot of unrelated sentences are with each other. So it pollutes the output. So what is one solution to that is a semantic chunking. What do we do is we take a large piece of text, we broke it down into sentences, and then we pass it to an embedding model, and we sort of cluster similar sentences together, and then we embed them together. You can read more about this later in this blog. Since this talk was mostly focused on evals, I'm just surfing through all of these methods now. And there's also contextual retrieval by Anthropic. What do? They do is they take all of these chunks and then calculate this context of this chunk with respect to the whole document, and they do it through an LLM. So that is why it might be a little expensive for you. If cost is not a big constraint, you can use this. And some of the heuristics and findings that I have come across is with you should never chunk too large. You should always have a maximum chunk size, because essentially what these embedding models are doing is they are compressing this huge text into a small fixed size of an array. So it means there is some loss of information. So if you chunk too large, the information loss is too much. It is not able to exactly encapsulate the meaning of a large text into a small array of numbers. So you should always have your maximum chunk size. It should be somewhere near to the length of an array, or somewhere. It should not be powers of magnitude higher than the length of an array of the chunking. And you should always include files and chunks metadata. What do I mean by that is, let's say some chunk ID, or which file this chunk is from, what kind of file was that. And also it helps when you use separator characters for splitting text, and sometimes that also gives good results. And yeah, last one is, don't try to not group unrelated information together. That is like the worst thing that you can do. Yeah, so we have our results here. uh, so its overall performance is good, and this is table that I've shown you guys. Yeah, I'll give a link to this repo at the end. And you should always look at your data. You should always have custom dashboards to look at your data, what kind of things people are doing, what is my F1 score, precision, mean recall, and any other metric that is relevant to you. And where these semantic embeddings fall short is, a lot of times in many embedding models, yes and no have a very similarity score of zero point 0.8 and zero point 0.9. And sometimes they're bad with nouns, right? And like, for example, if you ask how to spot a capybara in Amazon forest, it would perform extremely bad on only semantic search, because it would not gain the meaning of a noun, right? Sometimes we don't need a meaning of a noun, and they get confused when you group unrelated information together. And sometimes these embedding models which compress into a vector is called a dense embedding model, and they don't work where you have a organization specific vocabulary where that is not used anywhere else. So that doesn't have a literal meaning, but that has a contextual meaning in the organizations. And so what is the solution? The solution is good old hybrid retrieval and good old TF-IDF or BM25 embeddings that are called sparse embeddings. So here we use a sparse embedding model also, with the dense embedding model that we have used before. We store both of these vectors in the vector database. We store sparse vectors also, we store dense vectors also. And whenever user asks for a query, we get retrieved documents with respect to the dense embedding model. We get retrieve vectors with respect to the sparse embedding model also. And now what the problem is, we have, like, let's say 2 retrieved documents from each of these embedding models. How do we combine these 2 sets of documents? So the solution is Rerankers. Rerankers helps us choose the most relevant documents from dense embeddings and sparse embeddings. So they sort of combine them and re-rank the top ones, and then give only the top ones to the answer system and to the LLM. And this is a good re-ranker library, open source library by Answers AI. It's by Jeremy Howard, founder of Kaggle. It's really good. We use that in Iterate. And there's this also a method called semantic chunking. This can hugely decrease your embedding time, because in our use case, what we used to do is we used to embed a lot of code in our databases. And what happens is sometimes a lot of code looks very similar. People have similar functions for calculating date, formatting date, etc. And I don't want to hit embedding model again and again for the same embeddings. So what we did is we implemented semantic cache. So let's say text chunk, which I have calculated embedding earlier, is very similar to the text chunk that I've encountered right now. I just get that embedding from a KV cache and just store it in the model, store it in the my vector database. So there's an anecdote. We earlier our time was to embed a code repo 24.66 minutes, and then after semantic caching it was 0.61 minutes. So that gained us a huge performance jump, but it comes up with increased storage cost of KV cache. But yeah, that was fine. So this is the whole system after implementing re-rankers, sparse embedding models, dense embedding models, etc. One thing that another good way to actually improve your performance is rewriting query, right? So these are some of the products that helps you rewrite queries. DSPy is a really good framework for uh, programmatic prompting. So these are some of the options by LangChain, DeepMind, Microsoft, and DSPy. You should go and check that out for if you want to rewrite queries. It often helps you do that. And things you should always log is the rewritten query, mean reranker score, and a lot of user metadata. So let's say a query is really bad and the user drops off. You know which kind of user dropped off, what kind of users drop off due to bad performance, right? And now, congrats, you are in the virtuous cycle from the vicious cycle of prompting. And this is a good diagram by this guy called Hamel Hussain. He has a blog called Your AI Product Need Evals. It's really good. So now we have unit tests, we log traces, we have evals also. And then with evals, one superpower that you unlock is now you have a lot of fine data that you can fine tune your system upon. Yeah, that's it. Thank you. Yeah, if there are any questions, happy to answer. Yeah.
Thank you for the great talk. It's actually a really good change of pace to see people bringing evaluations and kind of like a test-driven development approach to
Yeah.
non-deterministic applications. My question is that if we are kind of integrating LLMs into our evaluation matrix anyway, for example, for synthetic data generation or at some point LLM as a judge, doesn't it create a case of who watches the watchman?
Yeah, it does. That's
So
why.
if it's a very large system, let's say
Hmm.
this is just two components.
Hmm.
Let's say you have n components in your system. You then need to evaluate the evaluators at some point.
Yeah.
And then it creates like another vicious cycle where you're like, who watches these LLMs?
Yeah.
So what's your opinion on that?
So with respect to the synthetic data, I did that because we do that to just get off the flying wheel.
Yeah.
The best way to probably have it as a human data or a
Yeah,
verified
yeah,
data.
absolutely.
And with respect to the LLM as a judge, it comes with an asterisk. So
Yeah.
you have to actually see if your model is better or not. And often what you can also do is you can have an ensemble of multiple LLMs, multiple critiques, and then you can do a weighted score of that as well. But yeah, it comes with that extra effort of actually making sure your evaluator is right.
Yeah.
But since the checking an answer is easier than actually generating an answer, it's a much easier task than actually generating an answer. So the errors are not that much due to my according to my personal empirical
Yeah, but you
evidence.
do see that there's a risk in a very large system where this
Yeah.
might happen.
Yeah,
where,
this
where
might
your
happen.
evaluators are itself not being evaluated. So
Yeah.
at some point you're kind of in that cycle of.
Yeah, correct. That's why a lot of people have built companies on top of
Yeah, exactly.
making these evaluators reliable.
Yeah, okay. So that's what I want to know. It's what's your opinion on that? I think thank you for the answer.
Yeah.
So I wanted to know, can we implement reranker in only semantic cache? And what was your approach if you did this?
In semantic cache,
Only semantic, without hybrid or sparse.
we can implement it. We did that as well, but we really needed it when there was two dense models output and sparse models output. Of course, it helps us with improving some of the performance, but it gives us huge dividends if we do it in different kind of embeddings, because re-rankers are also using an LLM behind the scenes and it has a cost to it. So the performance improvement was much more if we use those two embeddings together.
So in terms of evaluation wise, it is good. But if you are someone who is deploying application at large scale production, won't it slow hybrid queries won't slow down the result time?
It is happening actually parallelly. So it's not that it's sequentially doing the search. Like first it's doing dense search, then it's doing um, sparse search. We do this often parallelly. Like we do there's an option now in vector databases to do this hybrid search natively. So they have made a lot of changes in their sort of database infrastructure to make it faster.
Thank you.